talk about also what this model predicts is the concept of degeneracy. Okay, so degenerate states are different wave functions. So they're wave functions that describe different states, but those states have the same energy. Okay, so for example, so the way that this notation is written, those two numbers correspond to the different n numbers. So for example, if I wrote psi 1, 2, I would have root 2L, okay, times psi of 1 pi x over L times sine of 2 pi x over L. All right? And if we were to look at the energy solution for that, remember, that comes from right here, okay? Just adding up those two numbers, right? If n is 1, then it's 1 squared over L squared. And if ny is 2, then that becomes, 4 over Ly squared, okay? And also, if we assumed that the length of the x in dimension is the same, all right, then this energy level 1, 2 for the state psi 1, 2 becomes 5h squared over 8ml squared. Well, what if we switched the order of those n's? And not even really switching the order of the n's, but just literally making them different numbers, like a different state. So these are two different states right here. So psi 1, 2, psi 2, 1 are technically different states. However, if we look at the energy result for E21, it's the same as E12. So this is going to establish this notion that we call degeneracy. And this is going to come back later on when we're establishing even more physical reality, such as the atomic orbitals. As it turns out, degeneracy is really important in discussing the atomic orbitals. And what I also kind of wanted to show you, this figure right here, when you look at the psi 1, 2 and the psi 2, 1 state, the two states are related to each other by 90 degrees. So we could say they're orthogonal, right? They're different states. And I mean, literally, we can see they're orthogonal, right, by making them go 90 degrees. But they still have the same energy solution, which is very cool. So that makes them degenerate states, okay?